Alright guys, so this is going to be the video talking about chapter 21, which is all about carboxylic acid derivatives. Now at this point, Sati hasn't posted part 2 to her lecture, so I might discuss some reactions that she might not learn, which I think is okay because by the end it'll show up anyway. But I will cover everything on the part 1, but probably more. I'm going by the book as to what kind of reaction should show up. All right, so no time to waste. Let's get started. So chapter 21, all about carboxylic acid derivatives. What are carboxylic acid derivatives? Well, those are just anything that can be made out of carboxylic acid. So part 1 could be looking at some of these examples. So if we take a look at some of these examples, carboxylic acid derivatives will include stuff like acyl chloride. So we've seen acyl chlorides in the past. They were used for the last exam for your benzene reactions to add carbons. So that's an acyl chloride. By the way, all of these are going to look something like this. You generally have a carboxylic acid as a carbonyl with an OH, but a carboxylic acid has something else other than OH. So you have acyl chlorides, you have anhydrides, which is the X is a carboxylate, anhydride. You have your normal carboxylic acid carboxylic acid, so I'm just rewriting this because we'll see a pattern in a second. We have esters. We have amides. And one oddball is we have CN. So that's one of the weird ones, but it is true. So okay, the last two are not really new, but they have a different name. So let's discuss it. They're just a cyclic version of the ester and the amide. So first we have this one, which is called a lactone. Lactone is just cyclic ester. Meanwhile, the other one is called lactam, which is cyclic amide. Now, mind my writing. I'm going to try to do this fast, I guess, so the video is not too long. But you can, play it slow or whatever. Pause it. Okay, so this entire chapter is going to be all about how we can make carboxylic acids, some old methods of making carboxylic acids, alongside some new ones, and then how we take carboxylic acids and make these carboxylic acid derivatives out of those. We're also going to learn how to convert between various carboxylic acid derivatives. So it's a bunch of random reactions. We're going to use the scheduled sessions to ask any questions about this video or do practice questions. And also fill out a flowchart diagram making that I've made before. So let's get started. All right. We want to look at the pattern between these different derivatives. So let's look at this general pattern. Let's call it general pattern. General pattern. Now, because your test is a multiple choice test, you might get one of these questions where they ask you, oh, well, which one is more reactive? Which one is less reactive? And so on. So generally, our pattern goes something like this. If we look at the pattern for which one is the most reactive and which one is the least reactive out of these, well, it turns out that acyl compounds are the most reactive. Then it's the order I literally wrote them in. It's acyl compounds, then anhydrides. Then carboxylic acids are kind of equal or maybe a little better than esters. And then the worst or the least reactive are amides. So reactivity is going this way. Right now, this is most reactive. And these are least reactive. So again, reactivity kind of goes into if this thing is most reactive, it's because it wants to turn into something else. It wants to break apart. So going with that same structure, let's look at the base versions of if they leave, right? So you have this, you have a carboxylate, which looks like this. If this one leaves, you get an OH minus. If this one leaves, you get an OR minus. If that one leaves, you get an NH2 minus. So another thing you might see is that rank these with basicity and leaving group ability. So if you're the most reactive, it's because you want to leave. So Cl is considered the best leaving group in this case. This is leaving group ability. So Cl is the best leaving group and NH2 is the worst leaving group. And if you're a better leaving group, well then that means you're a really bad base. It goes opposite. Base really wants to add something. We learned OH is a good base. Why? Because it wants to connect to another H, right? So if you're a good leaving group, that means you don't want to connect to stuff, so you're a bad base. So this is the general pattern you'll see, and you can be asked a multiple choice question about this. Now, the question is, well, why is Cl a better leaving group than the others? The big thing we're looking at is electronegativity. Here, for these questions, we're comparing Cl versus oxygen versus nitrogen. Those are my big things. So Cl is considered the best leaving group or the worst base because it can handle negative charge really well. Why? Because it's the most electronegative. Cl is the most electronegative, then it's oxygen, then it's nitrogen. Thereby, chlorine is amazing leaving group. Why? Because it can handle a negative charge really well because it's electronegative. Then you have carboxylate, which is this thing. This can handle charge really well too. Oxygen is kind of electronegative. On top of that, this has resin, so it can handle charge generally too because of resonance, like that. Then we have OH and OR. They're like carboxylate, so they are oxygen, so they're kind of electronegative, but they don't have resonance. That's why they're a little bit worse than carboxylate. And then the worst is NH2 because out of these, that's the least electronegative. So it can't really handle charge really well. So it's considered like the suckiest as to leaving group. When we talk about leaving group or like if we talk about basicity, it's the best. But if we talk about leaving group, it's the suckiest one. All right, again, you should see a question either about most reactive to least reactive or one of these things, or maybe about like electronegativity. Okay, so I guess we're ready to dive into reactions. So starting off, we're going to look at some old reactions. Quick review for old reactions to make COOH. So some of the old reactions, if you remember, are something like this. So the first one we have is ozonolysis. We can do like a cyclic version of this or a linear. But if you remember, if you have ozonolysis with DMS, that normally cuts your double bond and turns into aldehyde. But if your second step is H2O2, then you don't go to aldehyde, but you instead go to a carboxylic acid. So here I would turn it into this carboxylic acid and this one right here. So that's one way of making carboxylic acids. Another way we've learned is another opening reaction. This is one of the newer ones, I guess. But if you have a ketone, this one is also opening your cyclic thing up. And this one's called HNO3 with like heat. And this one will also open up your structure and make the same carboxylic acid like we just did. Here, I'm going to make it like this because this is like hard to draw. There you go. You get the same answer though. Okay, here it's a little bit difficult. So the way you're kind of doing is you're kind of imagining if there was like a double bond right next to your ketone and then you just did ozonolysis. Now, if your thing is not perpendicular, then you can get two answers. So they really shouldn't be giving you a question where it's not perpendicular. Okay, part C. Another, one of the best ways to make carboxylic acids was if you have an alcohol or a aldehyde. Well, we learned that you can take those and put them through Na2Cr2O7 with H2SO4 and maybe like heat, I think. and that oxidizes them to a carboxylic acid. So any of the strong oxidizers, like the chromium ones. Now, for this, I think also KMNO4 works, if I remember. So KMNO4 with NaOH and heat will get the same thing as that. Speaking of KMNO4, we've seen this for benzenes. If you remember this reaction, if you have a benzene that has at least one benzylic H, so in this case, or let's make it a little bit smaller. In this case, there's a benzylic H there. If you take this and you put this through KMNO4 with NaOH and heat, it turned the entire R group into a carboxylic acid. So it turned this thing into a carboxylic acid, like that. So that was another one, really strong one. So just remember this one. Another weird one that you might have forgotten, this was in chapter 18, so it's like definitely important for this test, was Baeyer-Williger. If you guys remember, this one was the one where there was like that order where H was the most important, then like quaternary and then tertiary and stuff like that. This was done in just MCPBA. And again, H's took the most priority, and all we did for this reaction was just like we stuck a O in the middle. So again, because H takes the most priority, you end up making a carboxylic acid. So keep that one in mind. And the last one is actually one of the carboxylic acid derivative ones, which we'll see in a bit. But it was, if you have CN, you can put this through HCO plus and heat, and this turns it into a carboxylic acid, like that. So those are just some old reactions that we have learned that can make our carboxylic acid. We're gonna mainly learn how to turn carboxylic acids into new stuff that we know. So let's go about it that way. Okay, so the very first reaction we're gonna learn, I'll call this 4, I guess. 4. Alright, the very first reaction is gonna be how to turn acyl chloride into a carboxylic acid. So that's a new one. And actually, here, I can write this down. So we have like wordings. So acyl chloride 2COOH. That's the first one. So if we draw one of those, which we just drew, if you have this acyl chloride, well, to turn it into a carboxylic acid, like I said before, I said acyl chlorides are super reactive, right? I said they're super reactive because Cl can leave, because it's a good leaving group, because it's a bad base, it can just leave. So because they're so reactive, you don't need to do this in acid or in base. You don't need a catalyst for this. You literally just need water. If you have water, this will get the reaction done. Some of the side products we'll make is Cl- because it can chill by itself, and then we'll also make HCO+. Question is how, so let's take a look at the mechanism. So for the mechanism, step 1, you have your acyl compound, and we have water, so H2O. So the very first step will be to attack the spot, making this go up. This is completely irreversible, and we'll end up forming O-, OH2+, and Cl. Now, you don't want the water to leave, so the very next step is going to be to deprotonate. Next step, OH2+, O-. Another one of the water comes along, and it will deprotonate this H. So you have an OH, and you have an O- plus H3O+. And the very last step is to just deprotonate. To just kick off the leaving group. OH, Cl, so these electrons can come down, and the Cl can just leave. and we form our carboxylic acid. So you don't even need anything. You literally just need water and this reaction happens. So pretty simple. Any of the most reactive ones, which will include acyl chloride and anhydride, will just need water to turn into carboxylic acid. So that was our first reaction right there. Okay. Number 5. So next reaction. This one is how you go back. So I'm going to like I guess go over them together because it's pretty straightforward. So if you ever want to go backwards here, so let's write 5. We'll give each one a number. So number 5, this would be going from COOH to a acyl chloride. Or bromide. So we have a carboxylic acid. If you want to take a carboxylic acid and turn it into a acyl chloride, you just need to put it through SOCl2 with PUI. So we had this with alcohols, if you remember. Alcohols do the same thing. You just need SOCl2 and PUI, and it turns alcohol into Cl. Same thing here, carboxylic acid. So you can have that, or you can have PBr3 with PUI, and that turns it into Br. So that will make this one. So look out for this, because when we did the benzene reactions, you were always just given an acyl compound, or you were allowed it. Now you have actually learned a way to make it. So look out if they ask you for like how to do that. You know, an actual reaction that makes it now. Okay. So next reaction. Oh wait, I have to remember to like tell you this one specific reaction. Okay. So as for the mech of this one, it's actually super clear in the notes. So I'm gonna like divert you to the notes. I'm looking at it right now. It's on page 8. So look on page 8. It's only 3 steps long. It's pretty straightforward. I would just look at that one. I had learned it a little bit differently. It's essentially the same thing, but just look in your notes for this one. It's just 3 steps. It might be 4, but it's not that long. So, all right. You don't really do it with Br, but you do it with SOCl2, so you'll see it. All right. Let's go to number 6. All right. So this one's going to be how to turn anhydride into a carboxylic acid. By the way, in your notes, you have this one reaction called decarboxylation. I don't know why it was shown to you right in the beginning, but I'll do that one at the very end. So just wait it out for that one. And I'm going to make these like this, 1, 2, and 3. Okay. Anhydride to COOH. So just like acyl chlorides, if you want to go from an anhydride, which looks like this, to a carboxylic, you don't need much. You can just use water, because anhydrides are considered reactive. So in this one, you'll see that we'll actually end up making 2 of them. So one looks like that, the other one is that. So if this was like bigger, you'll get like another carboxylic acid. And then we also have water here. Okay, so looking at the mechanism for this one, step 1, we have this anhydride, and we have water. So water will attack this spot. Let's use a different color. Water attacks this spot, and this goes up. Reversible. Actually, just so you know, when Cl leaves, this is not reversible. I don't know why the heck I made that reversible. That's not reversible. Okay, so this comes back, and we end up making O minus and a OH2 plus. This stays the same. Step number 2, O minus, OH2. I don't want it to leave, so just like before, we're going to deprotonate this. Let's make that red. you get O minus and a OH and the double one O plus H3O plus. Okay, and step 3, which is the last step. You have O minus, OH, which will be, you drop this. So let's make it with red again. So you can drop this and then this goes away. This part is not considered reversible. So you end up making a O minus here, double bond O plus, you make a carboxylic acid. So as you can see, you might say, hey, you said the answer has 2 carboxylic acid, so one of them has an O minus. Well, this guy and this guy can react with each other, and this can just like pick up an H. So that's how you get the other carboxylic with water as a side product. But again, for both chloride and anhydride, they're pretty reactive, so all you need is water, and you'll go to the carboxylic acid, which is great. Okay. So, by the way, in the beginning, I'm just kind of showing you how to make carboxylic acid different ways. After this, we'll learn like how to convert these two other ones. I don't know why this is not making me draw this straight. Anhydride to COOH. There you go. Okay, number 7. Let's go to the next page. Okay, so this one's going to be ester hydrolysis. This is how you turn a ester into a carboxylic acid. All right, so ORs or OHs, like we said, weren't the greatest leaving groups, so they can't just happen in water. You can't just do that. You need to have a catalyst, and in our case, that catalyst will be a acid or base. So before we just needed water, but this one, we need at least a acid or base to work this. And lo and behold, you can do this in 2 ways. So if I have a ester like this, you can turn it into a carboxylic acid. And this can happen 2 ways. You can do it in acidic conditions like H3O plus, or you can do it in NaOH. So each one has its own mechanism. In fact, the base one is like the super easy one. And the acid one actually takes like some time. Now, I will actually point this out. If you do the base one, you actually don't end up with carboxylic. You end up with O minus, which you then have to put it through HCO plus anyway to make carboxylic acid. So like this one's like makes more sense. So like if you use this one, you'll end up with the O minus. So sometimes you don't want that. If you want that, then great. But all right, let's take a look at the mechanism for this. Step number 1. Oh, wow. Okay. Step number 1, you have this ester and you have HCO plus. So whenever we have acid and a carbonyl, we're going to protonate to activate. So this picks up the H and you protonate to activate. Plus O, that, and water. Step number 2. Now the water can attack. Now be a little wary because your test is multiple choice, you might not even get, like, I don't know how you can really test mechanisms. So maybe you don't have to worry about mechanisms too much. You can kind of just like watch this and like just like kind of understand it, and I guess it'll be like okay. But I'm gonna show it just in case because I got nothing else to do. All right, so you make that. Step number 3. HO, OH2. So you can guess, because we don't want that to leave, we're gonna deprotonate that. Like that. Okay, and now we want the OR to leave. So overall, like, thing is, we're trying to get this to leave, and we're trying to add another OH with this thing. So step number 4. We have this OH, HO. So let's protonate the ester now. We have HCO plus. So we'll protonate this. By the way, this one is completely reversible, so you can get it forwards and backwards. That's why the reagents are the same. So we protonate that plus water. Step number 5. We can now get rid of it. So OH plus. Alright, so this can go here and then get rid of my alcohol part. So now I have O with an H and a plus and a OH plus, and alcohol leaves like that. And the very last step will be to deprotonate that H. So this can pick up the H, and we get our final answer as that. So that would be the MEC if you were doing this in acidic conditions. Now, if this was given to you in basic conditions, it actually gets super easy. If you do it in basic conditions, which is actually also called sponification. So this is another like word they can use. Sponification. Sponification is when you turn an ester, and we're turning this thing into a O minus. That's what that is. So if we take a look at the MEC for it, again, all you need is base to do this, NaOH. If you look at the MEC, it's literally 2 steps. MEC, let's call it base. So if you take a look at this, step 1, you'll have this. And then we have OH minus, so lo and behold, you attack that spot, reversible. This goes to a O minus, this goes to a OH and a O ether, or O methyl. And then when these electrons come down, you can kick off this thing. So let's write another step, I guess. Step 2. So this comes down and then this leaves, yay. So as you can see, once we get this thing, you're not going to really stop here. Like you have this as an acid and this as an base. So this is why we get the negative. There's a little step at the very end where this actually takes this H off. So you actually end up forming what I showed you in the beginning. You end up getting a O minus plus HO dash. So look out for any tricks they try to pull with that. So again, if you want to do this where you actually form a carboxylic acid, you have to go base and then the acid right after. Alright, I hope that makes sense. Alright, so let's take a look at so that was how you go from that's how you break an ester, so go from an ester to a carboxylic acid. Let's take a look at a reaction that forms a carboxylic an ester. So I don't know what number are we at. Number 8. Let's do that. So number 8 is called esterification. It's how you make an ester. So this one's gonna be COOH to an ester, and it's actually just like the same thing, just backwards. So if you take a look at it, it's just reverse acidic like ester hydrolysis. So overall, you have a carboxylic acid. And if you want to go to an ester, let's say like an ester with an ethyl or something, all you have to use is that alcohol, whichever alcohol that you made, or whatever type of ester you made, with acid. And that gets the job done. Now, one of the side products is just going to be H3O plus, like that. So because it's the same thing as like reverse last reaction, we can kind of just like write this in a line. I guess it'll be easier. So let's do that. So we're starting off with this carboxylic acid, and we're starting off with an acid. So we'll start off with this thing. So the very first step could be you take this and you take this and you turn it into like OH2, and that's what we're going to start with. So very first step, we have a carbonyl with this, so you protonate to activate. So this can take an H and this goes here. You protonate to activate. And then my alcohol can attack. So this comes here. This goes up. Then another alcohol can take this H off. Okay, and then we want to get rid of one of the alcohols. So because we formed OH2, we can protonate this one. All right, and then we'll get rid of it. So this can come down and this can leave. Plus water, and the water at the very end can take off this H. And there we have it, esterification. Go from a carboxylic acid to an ester. It's pretty much the same thing, just like reversed. Nothing so special. Okay, so this reaction actually has, so again, you can do this with any kind of ester that you want, and like nothing big there. If you want to see more examples and stuff, come to one of the practice sessions. I'll make a bunch of questions, I guess, or I'll just like think of some and then we'll do those. But one of the, this is normally for making esters. Another one we have is like a special case for this. So we'll call this number 9. We'll call this a special case for making esters. Okay, so this one is if you have a carboxylic acid and our reagents are actually CH2N2. And it always makes the same carboxylic acid, which is with one CH3. You also release nitrogen gas as a side product, and whenever you let go of a gas, like nitrogen gas, this thing cannot be fully reversible. Okay, so if we take a look at the mech for this one, it looks something like this. You have this carboxylic acid, and we have CH2 like this, with a negative charge on it, and then N triple bond N with a positive charge on the end. This is why the entire thing is neutral, because you have a positive and a negative. So the very first step is this just takes an H off. This part is reversible. So you get an O minus, and you make CH3 N triple bond N and a plus. That's the first step. And the second step would be this. Since you have CH3 now and N2 gas ready to leave, you attack the carbon. You can attack this carbon and it can let go of the N2 as nitrogen gas. Oh my god. Okay, there you go. And this step is not reversible. And you end up forming OCH3 plus N2 gas. There it is. So mini special case, just so you know, if you see it as like a box, actually you don't have box questions, if you see it somewhere in the multiple choice. All right, now we are on number 10. Okay, there's a bunch of reactions. Okay, so continuing with the trend, number 10. This one's called amide. So we did ester. Okay, we did acyl chloride, we did anhydride, then we did ester. Now we're at amide. So amide hydrolysis. So this one's going to be turning amide into a COOH. Now, just like before, again, we said amides are not the best leaving groups because they're not reactive. Because they're not really that reactive, you can't just put this in water and it'll just work. So we need a catalyst. Just like before, the catalyst is either acid or base. So overall, if you have an amide like this, you can turn it into a carboxylic acid by having acidic conditions or basic conditions. And we're going to use the same principle. If you do the basic ones, you'll end up forming an O minus, which then you need to put through HCO plus to make the final answer. NaOH to make the final answer as OH. So what's the point of the basic one? I don't know. You tell me. But if they just give you the NaOH, you kind of need a minus there to be like completely correct, I guess. One of the side products you make is NH4, which is a salt. Whenever like nitrogen compounds get a positive like that, they end up turning into salts. Just so you know. Okay, so the reaction for this one is going to be the same exact thing that we did for all the other ones. It's literally the same thing as the one we did for ester. It'll be this exact same thing. So let's write it in a line again because it's easier. So if you take a look at the MAC, starting with this amide and H2 and HCO plus, the very first step would be to protonate, to activate. Plus and H2, and then we have water now. So the water then attacks. It's just like the ester one. Okay, now I don't want the OH2 to leave, so you do protonate. Now I want the NH2 to leave, so you protonate. Let me move this up a little bit. Okay, and then now you can kick it off. So this comes down, and then you can kick off the NH3. So since you have NH3, which is a base, this can take off the H, just like that. And you get your final answer, which is this, plus NH4, which is your salt, SALT. Okay, so that's your mechanism. It's literally the same thing like we just did, but with ester, like the one we did with esters. So you can pretty much just use that as a guide if you want to, but yeah. Okay, you can do this in basic conditions also. And that one is a little bit, that one is, let me take a look at the last one we did. The one we did in basic conditions. Okay, we attacked that, and then, let me think about this one. Okay, so this one's a little bit tricky because NH2 is not about to leave. So this one's going to have a little bit of a change. So if we take a look at the MEC, this was MEC acidic. Let's take a look at the MEC basic. It changes just a little bit. Okay, so if you look at the last one we did for base, when you attack with the alcohol, the O-ethyl, O-methyl can just leave because this can still stay by itself. But NH2 is not about to leave. It's not going to leave by itself. You have to turn it into NH3 to make it leave. It's not going to leave as NH2. So that's our little complications, which changes the mech just a little bit. So if we go step by step, the very first step is going to be you have your amide, and we're in OH minus. So OH minus just attack. So up till right now, the same thing. So you get O minus and an OH. Now, before for the other one, we said, hey, this comes down and this leaves. But again, this is not about to leave. It's not going to leave. So at this point, you can't just like have that leave. Instead, another one of the OHs is going to take this H off to form O minus and an O minus and an NH2 like that with water. This water is going to be used to protonate your nitrogen. So nitrogen's going to get protonated like that into a NH3 with a plus, and now you can get rid of it. So this can go here and this can leave. To form O minus and NH3. Now, just like before, you end up with the O minus here. And if you really want to form a carboxylic acid, you have to put this through acidic conditions right after. So just keep that in mind. Base. There you go. All right. All right, so this leaves us with the last derivative, and the last derivative was nitrile. So we're in number 11. Let's write this right here. This will be nitrile hydrolysis. So we're going to turn CN into a COOH. So just again, like before, you have to you can't just put it in water. You have to put it in acidic conditions or basic conditions. And we're going to do the same exact thing here. So let's take a look at both examples here. We did this before in the past, if you remember. If you have like a CN, we said, hey, you can reduce this to a NH2, or you can oxidize it to carboxylic acid. I discussed it right in the beginning too, if you remember, right here. A CN can be turned into a carboxylic. So now we're actually like looking at how it works. So let's draw it out. You have, let's say, this CN, and you can turn it into carboxylic acid. And you can do it in acidic or basic. So H3O plus. You need heat with this one, or you'll often see the heat sign with this one. And then you can also do this in base, and just like before, you'll have the same problem with O minus. NaOH with heat, and then you'll make O minus, which you can then turn into carboxylic with HCO plus. There you go. Okay, so let's take a look at the mech for this one. This shouldn't be like the other ones. It's a bit different, right? So, because you don't have that carbonyl or anything. So, it might be a little trippy to look at, but let's look at it anyway. So, this will be the mech in acidic conditions. Let's keep writing in a line because I'm kind of like going used to that now. Kind of liking it. It's much easier. Okay, so let's take a look at it. We're starting off with the C triple bond N like that, and we are in acidic conditions, H2O plus. So the very first thing you do is you protonate this nitrogen. C triple bond N, and we get a positive here. Cool. And now we have water. So our water is going to be the source to adding carbon. So this is going to attack this carbon right here, making these electrons go here. So I'm going to draw this below here, OH2 with double bond N, like that. Hopefully that makes sense. Okay, now again, just like always, if you don't want the water to leave, you better deprotonate it. So we're going to use another water to deprotonate this. And we'll form, oh my god, this is so annoying. Okay. God, this is annoying me. Okay. Up, N, H, OH. There you go. Okay, so you deprotonate it if you don't want it to leave. And we also made acid again. So H3O plus. H3O plus. So we're going to use that to protonate the nitrogen again. So overall, if I think about it, this reaction kind of goes like this. If I draw this little intermediate, what happens is I'm showing you the mechanism of how this turns into an amide. Once it turns into an amide, we'll be in acidic condition still, so we'll go all the way to the ending. You can't really stop in the middle, and you get the final answer. In reality, I'm just showing you the mechanism from here to amide. After that, it's just happening, whatever's happening is what I taught you right here. So let's go. Next step, I protonated that, so I will form double bond NH2 with a positive and a OH, like that. Okay, now you can have these electrons. As you can see, there's a resonance structure here. These electrons can go here, and this can go over here. So if I draw that resonance structure out, I will have double bond OH plus NH2 with a negative like that. No negative like that. Just like that. All right. And the very last step for us will be to deprotonate that H. So we're going to have one of the waters do it. When this got deprotonated here, that's where we formed the water, by the way. So the water will take that H off at the end. And that's how we get the amide. This, and because you took off the H, you have H3O plus. Now notice this, we have amide now and we have acid. So you keep going until this turns into a carboxylic acid. You don't stop here. You're just putting in the next set of steps to turn it into carboxylic acid. So this will technically keep going until the COOH. All right, so that's nitrile hydrolysis in acidic. In basic, let's take a look at how it works in basic. Mech, now in basic conditions. Cool, so just like before, it's going to be a little bit shorter. We're going to also, again, just look at how it gets to amide, and then we're done. So, step 1, you have this C triple bond N again. And we have OH minus, so because you have OH minus, you can directly attack, and this goes here. This part is reversible. C double bond N with a minus here. And then I can call this OH, like that. Then you have to have water. So with NaOH, it's actually a bit different. I think you need water in this one. H2O. Yeah, that seems right. So you need water in this one. It's a bit different. Okay, if you have water, H2O, that's when you protonate this nitrogen. And you make OH minus again. So the OH minus will take off your H from the oxygen. Can I make this go higher? Let's keep it there. So once you take off that H, you'll get O minus Dovan and like that. So once you take that H off, you have resonance here, like before. So if you take a look at this resonance, you can bring these electrons down, and then this can go here. That's your resonance structure. We also formed water again, just so you know. So resonance structure looks like this: double bond and H with a negative. And the very last step is going to be to protonate using the water we just made. So this nitrogen can pick up the H from the water, and we get our amide. Plus NaOH. So like before, because we have amide and NaOH, we're going to go all the way to the ending until we get like the COO minus. But essentially the same thing. Forming the amide. And the NH4 and the Cl can combine together to form your NH4Cl salt. Like that. Okay. The next one is, so that was that. The next one we're going to do is how to turn acyl chlorides into esters. That's number 13. So acyl chloride into a ester. Okay, so if you want to do that, all you need to do is put it through the ester alcohol that you want, and you need NET3, so a base. And that turns it into that. Now here you also form a salt with NET3. You form this salt plus NCl minus. That's a salt. Alright, so if you take a look at the mechanism here, it'll be very similar to the one we just did. You have your acyl chloride and you have an alcohol. So this just attacks the spot. This goes up. You end up getting O minus and a OH methyl with a Cl and a positive here. Then this is a spot. This is like the point where you explained why you needed the triethylamine. So if you use another one of the alcohols to take this off, you'll form this thing right here. And then this thing, after, when you get the Cl, can react with the Cl to like take the H off. When you do that, you'll have HCl and you'll have acidic conditions. And it turns out if you have acidic conditions with the acyl chloride, you'll just turn this into a carboxylic acid, which is like not what you want. So if you don't want the carboxylic acid there, you have to use a better base than another alcohol. So that's why we use triethylamine. The triethylamine will take off that H. We get O-methyl, Cl, and then the very last step is this goes here and this goes out. And you form the salt on the side. So just remember that's the primary reason we use the triethylamine there. Okay, the next one is anhydride to an ester. Now again, these are a lot of reactions. Most of them are doing the same thing over and over again. What I would tell you to do is use this video and her notes, and then whatever's in her notes, you can kind of like quickly mark on this video or like on these notes, and then only learn that stuff. Anything that's not in her notes shouldn't really be on your test, so I wouldn't worry about it if it's not in her notes. Number 14. So this will be anhydride to an ester. That's your anhydride. If you want to turn it into an ester, all you need to do is put it through an alcohol. So let's say we use ethanol. Well, that's going to turn one of these guys into ethanol, or this ester, and the other thing will turn into a carboxylic acid. Like that. Looking at the mechanism for this one, very similar to all the stuff we've been doing. You have this anhydride, and you have this ethanol, so this will attack this spot. This goes up. Have I been making the... Okay, so really quick, these reactions that I've been doing, the very last step should not be reversible. These don't go backwards. Whenever like a chlorine leaves and you form a salt, you're not going backwards. This was supposed to be one step. All right. Okay, back to this. We have Dovon O, O minus, OH, and ethyl plus. Okay, once you get that, then once you get that, you can use another one of the alcohols to take this H off. Like that. And the very last step is going to be, so we also form OH2 plus here. The very last step is going to be this goes here and this comes off. So you form O minus here plus you form the ester on this side. So this guy and this guy can be used together to, you know, pick up the H to get the other carboxylic acid. But we just needed the ester, and that's how the ester is formed. Okay, next reaction. This one's called transesterification. This one's actually quite simple. 14, 15. It's called transesterification. So that's just if you want to go from one ester to another. So ester to another ester. So let's say I had this ester and I want to turn into like one with ethyl or something. Well, you just need that alcohol with acid and you'll turn into that. It's really straightforward. Nothing to like worry about on this one. And that would be your side product. So quick example for this one would be like, let's say I had this ester again, and imagine if I put it through like this, okay, with HCO plus. Well, then you'll end up forming this, OH. And then another answer, like if this reacts again, you'll get another answer which looks like this. I missed the O. Like that. But pretty straightforward. Okay. Next reaction is to turn anhydride into amide. This is like the same exact reaction for a mechanism for acyl chloride to amide. So we don't really have to write this one out, the mechanism wise, but I'll just give you the reagents. Again, this looks like a lot of stuff, but most of these mechanisms you might not even need to know, because like how can they test a mechanism on a multiple choice? So number 16, we have anhydride, also like the flowchart diagram I've made, that will really help you guys. I kind of just used the flowchart diagram to like help me throughout this entire chapter when I did it. So this one's going to be just like acyl chloride to amide. If you have a anhydride like this, You can turn it into an amide by just putting it through the nitrogen compound. So let's say I put it through this. Well, then you'll end up getting that amide. If I put it through NH3, it would turn it into NH3. The side product is this. You have O minus, and then you have H3N plus, like that. But the mechanism works exactly the same, so you don't really have to do it. Now, if you put this through NH3, let's take a look at that one. If we put it through NH3, then we would just end up getting NH2. That's your amide. But if you want an R group, you can have like an R group attached to it already. This plus the other amide. There you go. With H4N. Just like that. Okay, so that's anhydride to amide. And then we have esters to amide. So number 17 is ester to amide. If you have an ester, you can turn it into an amide by, again, just like before with this one, you can just do that with NH3 or whatever R group you want on it. So we're going to use NH3, and that gets the job done. So the side product here will be, this comes off, so you end up forming HO that. So imagine if we had like a lactone or something. Let's say we had this, and we do NH3. In this case, you'll end up forming and NH2 over here, and then your alcohol's attached to your thing, so like that. But pretty self-explanatory. All right, and then the very last one we have is acyl chloride to anhydride. This is the last one I have. And then we have like some random other reactions, but not like the derivative ones. So let's take a look at number 18, which is acyl chloride to anhydride. Okay, so if you have acyl chloride, you can turn it into an anhydride if you put it through NaO that. So you just have to put it through that thing, and because Cl is a better leaving group, it's gonna make it leave. So if you take a look at the mech here, by the way, the side product here is just NaCl, if you want to know. So if you take a look at the mech here, we have this acyl chloride, and this thing can attack. So this thing will just go here, this goes up. Because Cl is a good leaving group, when this comes down, the Cl will leave. Whenever a better leaving group leaves, this is like not reversible. Hopefully I did not make a mistake with that anywhere else. Cl minus, like that. Chlorine's a better leaving group, so it's gonna leave. Pretty straightforward. Okay, so that's all of them interconverting with each other, making carboxylic, how to turn carboxylic into them, blah, 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 blah. Okay, some little things to know on the side, which are going to help you include the Grignard reactions, how they're going to react here. And the very last thing is this decarboxylation reaction. So let's look at number 19 and 20 as that. So first, let's take a look at Grignards. Okay, so if you remember when we had a ketone or an aldehyde, right, and we put this through, let's say, this MGBR, we usually had the second step as like acid or something. You just attack this spot and this goes up, right, and then you protonate using the H3O plus. Right, so you end up getting something like that. Or if I like draw it better, it would be something like this, like that. So the thing is, like, aldehydes and ketones don't have a leaving group, but carboxylic acids do, right? So carboxylic acids or esters or acyl chlorides do. So the two we're going to look at here are acyl chlorides and anhydrides, because they have really good leaving groups. So acyl chloride, I'm going to write on this side, and anhydride. Okay, so if you take a look at the same example here now, if you have an acyl chloride like this, and I decide to put this through a MGBR, think of what happens here. If you like think about the mech here, you're gonna attack this spot, and this goes up, right? Okay, pretty straightforward. So if I draw what that like looks like, you end up getting an O minus, and I just added those carbons, and then you have a Cl. Okay, but then can't this just come down and then kick off the Cl? It can, and it will do that. So once it does that, you just added carbons, and then you have a ketone ready to go, right? So you end up making this, you reform the ketone. But then I still have more MGBR left, so this MGBR can attack again, and this can go up again. So once you do that, and then you end up getting an O minus, and then another ethyl attached. So overall what we learned here is if you have an acyl chloride or even an anhydride like this, you overdo the reaction. You can't stop halfway. You can't just add once. You have to add twice. Here in this case, it would be like you attack that spot, this goes up. When it comes down, this entire thing leaves. So if I draw that out, you'll get O minus. You just added these two new carbons. But then when this comes down, this acyl chloride or this anhydride thing just leaves. So I added carbons, and I like formed a ketone. Like this, and then this thing just left O minus with this. But I still have more MGBR, so another MGBR can attack again, and then this can go up again. So both of these overdo the reaction. Okay, and you have to keep that in mind. MGBR and Li will overdo their reaction. Okay, you're going to keep adding for both acyl chlorides and anhydrides. However, and again, you need like the H3O plus as the second step. So otherwise you stick with the O minus. So let's write H3O plus as the second step to turn it into a carboxylic acid at the end. OH at the end, sorry. H3O plus. Okay, so those two overdo their reaction. However, if you instead decide to do Gilman, so which was CuLi, so let's say instead I have this as the question. This won't overdo the reaction. Let's say I have this thing, CuLi, and the second step is water or HCl plus. This won't overdo the reaction, and you'll actually stop after you add those two carbons. So the final answer here will be this. MGBR and Li will overdo the reaction. Let me show you an example again. The same example we used here. This answer is actually this. You go all the way to the alcohol. But if you do CuLi or Gilman, won't overdo the reaction. So I would remember that. Just like this. Okay, so that's how you're going to use carboxylic acids and their derivatives. That's where you're going to use the MGBR to attack and stuff. The very last reaction we have here is decarboxylation. Again, I don't know why it's given to you right now. It's more of like a later on reaction, but since it's in your notes, I'm going to kind of like teach it. Decarboxylation. By the way, again, if you want practice questions for all of this, including that flow chart, just come to one of those like practice sessions and we're going to do like practice there. Hopefully I can make it in time for tomorrow. Or like make enough practice questions by tomorrow, but yeah, if you just want practice for it, just come to that. And also, maybe you don't need to know all of this information. Just look through her notes and match whatever is in her notes. If it's here and in her notes, then you need to know that stuff. If it's not in her notes, ignore it. Okay, so this decarboxylation reaction, it has some requirements, and those requirements are you need to have a beta carbonyl. There's 3 requirements, or beta carbonyl. You need heat, or let's see, beta carbonyl. What else was it? You need a carboxylic acid, and you need heat. So imagine if I have this carboxylic acid, and exactly this is considered the alpha spot and this is considered the beta spot. So if at the beta spot you have a carbonyl, which in this case you do, and this reaction happens in heat, well, then you're going to decarboxylate. So what is decarboxylation? Well, this thing right here will turn into CO2, okay, and dip. It's just going to leave. So the way you kind of like quickly do this reaction is you pick up whatever molecule you have, you kind of like circle any carboxylic acids you find, then you label the alpha spot to the carboxylic and beta spot to the carboxylic acid. If at the beta spot you see a carbonyl, you're going to chop this entire carboxylic acid off. If I chop that off and replace it with like a H or something, right, that's your answer. So here my answer would be this ketone plus I chop that off, so I get CO2. Now, if I give you another question here, let's say I had this big thing. So let's say I had this big molecule, and then this is in heat. Let's go through the steps. Let's circle any carboxylic acids we have. So one is right there, one is right here, and then the last one's right here. Right. So let's label the beta spots for those. So this is the alpha spot, right? And this is the beta spot. This is also a beta spot, but this one has a carbonyl. So let's use that one for this top thing. Okay. Since there's a beta carbonyl there and we're in heat, this thing is getting chopped off. All right. So all of this is getting chopped off. Great. Okay. What about this one? This is alpha and this is beta. Is there a carbonyl there? Nope. Okay. Because there's no carbonyl there, this is going to be ignored. What about this one? This is the alpha spot and that's the beta spot. Okay. So this gets chopped off. Already saw that. My final answer should be everything except what I like chopped off. So it'd be like this. Up, this. So you would get this, and because I chopped off 2 carboxylic acids, I get 2 CO2. Like that. That's the very last reaction. I don't know if you need to know the mechanism for this one. I can quickly check for you. You might need to. It's like a step or two. I think it's literally like one step. It's like ketone to enol. So if you want to look at the mechanism, look in the notes, but you shouldn't really get the mechanism for this one. This is totally like doable question for a multiple choice. So look out. But it's pretty straightforward. Again, if you need practice with any of this, just like I'll try to make some questions and stuff. The first thing we're probably going to do is like the flow chart diagram thing I've made to help you understand this better. But overall, I think most of the reactions are very straightforward. It's just there's a lot of them, so you gotta like remember what does what. And if you understand like the chemistry, acyl chloride is more reactive or like anhydride is more reactive, then it becomes kind of easy. So again, if you have any questions, let me know, and stay safe. Bye.